Hello to everyone, and to talk today about BridgeSwitch, which is PI's motor driver IC family. My name is Cristian Ionescu Catrina, and I will be your presenter today. We'll talk a bit about the market trends and what drives brush SDC and inverter demand. Then go deeper into the BridgeSwitch architecture and unique value against discrete and IPM, like highest efficiency, hardware protection, and built-in diagnostics. Have an overview of the design tools and the summary. Okay, so let's get it started. Improved energy efficiency regulation is the main driver for change to brush SDC motors and advanced drive techniques like inverters. Let's go through some examples. Energy Star appliances saves cost and energy. With the new eco-design energy regulation, EU wants to save 20 billion euros in energy by 2030, which is an ambitious goal, only possible by making a couple of changes to the current standards. So they added low power motors starting from 120 watts. Before it was around 1 horsepower, and this opens the way for new applications to be more efficient. And they also added single phase motor efficiency, which needs to meet IE2 levels starting 2022. There is also a new EU energy labeling, which is mandatory starting 2021. It will simplify labeling and consumer decision making, but will also raise the efficiency level. For example, in the case of dishwasher, they will be required to be 30% more efficient. Similar targets also in China with the new GB regulation, which sets new efficiency standards for HVAC, came into effect July this year, and the previous best-in-class efficiency is now second best. BLDC motors and inverter control also provide more accurate motor control and reduces audible noise, which are key customer care abouts. But performance needs to be balanced with system cost. Three-phase motors require 6 switches for the 3 legs and can be relatively expensive for some application, particularly when we consider the software complexity. Single-phase motor on the other side are simpler, have a simpler motor design, only uses 4 switches, and is a more cost-competitive solution, delivering high efficiency and performance. On top of that, customers also need to innovate. For example, Bosch Siemens announced in September a new concept called System Master, which is in fact a new microprocessor which turns the appliance into a digital service platform. This will allow the service center from Bosch Siemens to remotely diagnose faults into the appliance and fix them. We'll talk later how BridgeSwitch can enable such use cases. Let's look a little bit into the BridgeSwitch architecture and the benefits. BridgeSwitch is an integrated half-bridge solution with both low side and high side. So the gate driver, the matching circuitry, the FretFET with the built-in body diode. At the core of the IC, we have the 600 volt power FretFET with very low RDS on across the different variation in the product lineup. It has an optimized body diode inside the FretFET structure, which has been designed with low EMI and low QRR losses in mind. Very important is that the device is factory trimmed, has a factory trimmed gate current and slew rate control, which means that the performance of the part is very predictable across the entire BridgeSwitch population of devices. And this also means that the designer doesn't need to spend time on matching in between the gate driver and the FretFET. They can focus directly on their use case. BridgeSwitch also reduces the software development or certification time by at least 2 months. And this is possible because of the Class A software readiness, according to IEC 6730. BridgeSwitch doesn't rely on software per UL report you will find on our website. Another care about for the designer is system complexity. BridgeSwitch doesn't need the external shunt for the current feedback. We will talk about that later. It exposes the motor current which flows through the low side FretFET to a pin called IPH. This doesn't require, as I said, the shunt, only needs a very small signal resistor. This also means that there is no need for op-amp because all of the amplification is done inside the part. Now, the two PWM inputs, INH and INL, can be tied together in some cases, which will reduce the number of PWM outputs from the microcontroller from 6 to 3. This means that in this case, the microcontroller is simpler, the software is simpler, so the total cost of ownership is smaller. Now, uniquely in this market, also BridgeSwitch has an integrated high voltage bus monitoring. Most of the solutions out there, either they are IPM or discrete, require a shunt connected to the high voltage bus and the associated circuitry, including op-amp, in order to continuously monitor the high voltage bus. This is not needed with BridgeSwitch. It has this built-in feature already, and it notifies the MCU of what's happening on the bus. As I mentioned before, there are a range of services which are on the rise. One of them is predictive maintenance and remote diagnostics. BridgeSwitch has ability to report the status of the IC itself and of the system through a one-wire bus, which is called fault bus. And it's also, the architecture is ideal for both single-phase and three-phase motor, with 2 ICs required for single-phase and 3 required for three-phase. And a very simple way to identify the leg through an ID pin, which uniquely identifies each of the leg. So on top of that, it's a very flexible architecture, works with both 3 and 5 volt MCUs with the most popular microcontrollers and algorithms like field-oriented control, trapezoidal or sinusoidal. Very important is the bill of material. So only 20 components are needed for three-phase designs and 15 for single phase. Let's take a deeper look into the functionality for a three-phase system. We'll look only into one leg. The functionality is similar for the other legs. BridgeSwitch low and high side drivers have integrated high voltage current sources. This which allowing it to supply itself without external supply. Both taps connect to the HD pin and they provide sufficient drive current for the FretFET and supply current for the driver IC. Then we have 2 bypass capacitors for the low side and the high side, and they must deliver sufficient gate charge to turn on the FretFET and to provide bias current for the gate driver low side and the high side. BridgeSwitch also has an internal shunt regulator which allows supplying it externally in case self-supply is not suitable. The device monitors currents throughout FretFET independent from the microcontroller or any external circuitry or the software. The cycle-by-cycle current limit is is set with external resistors here RXH and RXL, and is done independently on the high side and low side. The current limit is adjustable with the maximum value found in the datasheet correspondent to the part number. When the value is exceeded, the respective FRET will stop switching. For example, on the high side will stop switching, and it will report the fault condition over the diagnostics bus, fault bus, to the microcontroller. And in response to that, the microcontroller can take action, for example, by turning off the complete inverter. There is also a pin here called system monitor pin, which can be used in 3 different configurations. One is monitoring the high voltage bus through this resistor, and it can provide different trigger levels for UV and OV protection. Another way of using the SM pin is to monitor an external NTC. It's also trigger based when, for example, 150 degrees Celsius has reached, the BridgeSwitch notifies the microcontroller through the fault bus. You need to imagine all of these 3 bridge switches. Each one have, of course, the fault bus pin. All of the fault pins are connected to each other, and through a pull up to a 3 or 5 volt rail. It's similar to an I2C bus. The differences are two. One is there is only one wire, not 2. And secondly, also the slave can, in this case, the BridgeSwitch can initiate the communication. The driver software which is required to implement this capability on the microcontroller is very small, around 2 kilobytes flash and 30-40 bytes RAM. The third feature of the SM pin is to attach a custom sensor, for example a vibration sensor, same trigger-based functionality as we described for the external NTC. Now, also the BridgeSwitch provides the current which flows, the drain current which flows through the low side FRET, which mirrors the current which flows through the winding of the motor. In this case, the user doesn't need to add an external shunt, what is required with the competitive solution, only needs a small signal resistor which is used to amplify the signal which is then sampled by an ADC input on the microcontroller. There is no need for an external op-amp. So such configuration, of course, reduces the system cost, provides a better efficiency by removing the shunt resistor. Now, looking at the lineup, we have 5 different families. Each one has 2 flavors. So for sake of simplicity, I refer to each family by calling the last digit. For example, size 0 has a continuous RMS current of 200 up to 220 milliamps and is suitable for application up to 50 watts. The 2 flavors within the family refer to the 1.1 and 1.2 series. The only difference is that the 1.2 series has the IPH pin and the 1.1 doesn't. All of the other features are available on both parts. Size 1 can deliver up to 500 milliamp RMS and 100 watts, up to 100 watts designs. I also wanted to add here the DC output current, which is in general the metric used by the competition in their datasheet. It's not a relevant metric for designers because it doesn't have a real, let's say, meaning when it comes to real value like RMS. but it's important for you when you are trying, to make an equivalent of an existing solution to BridgeSwitch. Size 3 is suitable for application up to 200 watts and RMS 750 milliamp. Size 5 300 watts and size 7 400 watts, particularly for thermally challenging applications or applications which require RMS current up to 1.3 amp. Very important is that all of these families share the same package and the same pinout, so it's very easy to swap in between. And as you can see on the bottom side, there are two exposed pads. If you can create a mental picture, those are just underneath the fret FET. So there are the two fret FET here, and underneath them you have the exposed pads, which help to dissipate the heat which is generated within the fret FET. The reason for creating this package was to remove the heatsink. We are using these exposed pads to dissipate the heat through the PCB, and in this case remove the heatsink and remove not only a cost component but also remove the manufacturing cost and increase the reliability of the total system. In terms of applications, BridgeSwitch is suitable for both single-phase and three-phase designs, different type of motors, fan, pumps, and compressors. I'll give you some example. Axial fans in industrial application, or centrifugal fans for both, and radial fans for both industrial and residential, commercial aircon, commercial HVAC, range hood, fridge compressors, but also heat pumps, industrial pumps, pumps also in washing machine, water pumps, or dishwasher. So a wide range of applications. Important to keep in mind, 400 high voltage motors up to 400 watts. Certification can be a significant time and resource consuming process, especially when it involves a completely new product to be certified. So companies want to reduce time to market, and certification can push this out by 4 to 5 months. With the BridgeSwitch, which is Class A software ready, the customer can cut the certification time by at least 2 to 3 months. The feature which enables that is the cycle-by-cycle current limit protection, both on the low side and the high side, which protects the inverter and the motor. Within the fret FET structure, there is a sense FET which provides this monitoring and protection. And the overcurrent threshold are set, as we discussed, by these two resistors. There is a range of to select the current level from 100%, which is a maximum per device size, from size 0 to size 7, to 43% by carefully selecting of the values of these resistors. It also have fail-safe implementation. BridgeSwitch also monitors for short circuit or overcurrent faults. There is no software interaction required to trigger the protection. This is an intrinsic built-in hardware protection which works cycle by cycle. When the current limit has been reached or has been exceeded, the fret FET switches off. There are two use cases here. One is what I already mentioned, meeting the regulation and the IEC 6335 and 6730, and in fact being able to pass the certification much faster. The standard solution out there on the market, whether they are discrete or IPM, don't have this hardware built-in protection and hence require the software to take action. That is why they are in what is called Class B software. A Class B software solution requires more time to develop and longer time to certify. Another use case is, are fault conditions which the customer needs to protect their application against. For example, stalled motor, disconnected motor phase, or running overload. All of these are possible to enable with BridgeSwitch without software intervention. A study showed that 30% of HVAC and fridge compressor repairs are no fault found. This is due to lack or misdiagnostics and generates unnecessary costs throughout the supply chain. Current motor driver IC solutions don't have the capability to specifically monitor and report what is wrong and where. Let's look at some system faults. Surge or fluctuation of the high voltage bus, excessive current and temperature of the inverter, it gets too hot, power switch failure, mounting issues of the heatsink, unwanted, which of course has implication on the thermos and current, unwanted motor vibration, which over time can damage the motor, winding shorted to ground, stalled rotor or motor overload. All of this can over time lead to damage or reduced performance, damage of the inverter, of the motor, or reduced performance. To cope with these challenges, a traditional inverter needs external sensors and processing power. But this means extra cost. With BridgeSwitch, it doesn't need to be like this. BridgeSwitch will identify affected phase in case any of the previously mentioned fault will pop up, activate protection, inhibit switching, send fault identifier, and then re-enable switching. It also sends over the Diagnostics bus up to 9 distinct messages: UV, OV levels, thermal warning, thermal shutdown, the low side and high side overcurrent, pin level faults and threshold faults like we talked about for the vibration sensor, but also insights into the readiness of the inverter, device ready or device not ready. The MCU knows at every time what's happening with the inverter and in the system. So it can log this data and maybe push up the data, do either smart diagnostics on the edge or push up the data to the cloud where a service center can consolidate, can aggregate it and monitor the appliance health status. Let me give you some examples of the design wins and the reasons for that. For a pump design, the customer was using a 3-phase brush SDC with discrete. However, they felt like they spent too much time in matching the discrete solution, and also the bill of material, the solution was too bulky. So they changed to the BridgeSwitch solution. They achieved a simpler bill of material, hardware protection without software intervention, and they were able to come to market much faster. For the range hood, the customer was using single-phase ACIM with the triac, but they wanted to enter the higher end segment with higher ASP. This was only possible by offering new functionality. So they replaced the triacs with the BridgeSwitch. So they still kept the single-phase ACIM, but inverter driven, and they were able to achieve lower audible noise and variable speed control. For a centrifugal fan, very important is the space constraints and to meet the thermals because the PCB is inside the motor. Customers are using single-phase BLDC with discrete. By using BridgeSwitch, they reduce the bill of material and the system complexity. They are also able to connect the PWM inputs of the BridgeSwitch together and reduce the number of the PWM outputs on the MCU. In a nutshell, BridgeSwitch is the best solution for motor drives. Against the IPM, it has higher efficiency due to the excellent body diode. It doesn't have hotspots. IPM has all of the 6 switches in one package. It is much hotter under high current test conditions. And IPM doesn't have intrinsic monitoring and protection features. It requires the microcontroller and the software to take the lead. And because it has all of the 6 switches in one package, not only the reliability is lower due to the hotspots, but also requires heatsink. With the BridgeSwitch and the ability to have a much cooler package and a better efficiency, we can remove the heatsink, and we can also enable a more simpler system design with self-supply. Against the discrete, BridgeSwitch offers higher integration, doesn't require matching, and has a hardware-based motor for protection, with minimum external components compared to the discrete. There is also a wide range of inverter reference designs, which are suitable for many applications. As you can see here, we have single-phase designs. We have a lot of three-phase solutions based on the different part numbers, so covering different power levels from 30 watts to 400 watts. When efficiency is key, you can take a look here and pick the right design for the application. Some of the design already have a built-in microcontroller, like for example the 653 with the Toshiba FOC ready MCU, and the 749 with the Princeton microcontroller, which is a Taiwan-based company. All of the other ones are very flexible in enabling the customer MCU card. So the way to do that, we have defined, particularly on these boards from A51 down to the 873, we have defined an MCU interface so that the customer can quickly swap in between cards and still keep the same pinout in between their MCU card and the target motor driver board. So applications are from low power, lower current ventilation fan and centrifugal fan, up to more challenging application like garage door opener or industrial pumps and compressors, or maybe thermally challenging applications like, for example, we had recently a range hood industrial motor driver solution, where the ambient can be as high as 70 degrees Celsius and the package temperature is not allowed to exceed 95 or 100 degrees. So a temperature rise of 30 degrees Celsius. So first of all, please check on our website. All of the design boards I mentioned before are available. We are in full production. We have secure supply, and besides the board, a comprehensive design support with application note describing design guidelines and troubleshooting, single-phase theory, control, and the BridgeSwitch advantage for customers who don't have so much experience with single-phase. But also we provide C-code example for the diagnosis bus. This is very important because it offers a very quick path for the customer to integrate that in their application. We have also a range of white papers, the UL report with the compliance to the safety standard, the IEC 6730, and the package information and IR reflow process. In a nutshell, BridgeSwitch is uniquely positioned against competition. It has excellent efficiency due to the ultra soft body diode. It simplifies the system by, for example, removing the external power supply. by removing the software from the certification loop, and with the single wire interface communication called fault bus, it provides insight into the inverter and system health, which can help use cases like remote diagnostics. It's a very flexible solution, works very easily for single-phase and three-phase motor, and has a very low profile surface mount package. In fact, all of our boards, design boards, which we mentioned before, have a very good description of the size of the copper area which is required in order to cope with the dissipated heat. So please check them and align with the customer what size of PCB copper area is acceptable to them. So I would like to thank you for your time, and we are looking forward to working together with you to find the BridgeSwitch projects. Thank you.